So today we're going to finish up chapter 21. We're going to do sections 21.14 to 21.17. So the first thing we're going to add to aldehydes and ketones today is alcohols. So we have alcohol addition. And the cool thing about alcohol addition is that it acts a whole lot like hydration, like adding water. So if you have a ketone or an aldehyde, and you add an alcohol, say ethanol or methanol or isopropanol, with acid, so it's acid catalyzed, your first step is going to look like this. You're going to end up with what we call a hemiacetal. So you have an OH on top, which came from the carbonyl, and then you have the OR on bottom, which came from the alcohol. The difference between hydration and acetal formation is that you can additionally add another alcohol. So this is always going to happen. And in the second step, you'll end up with two alcohol groups instead of just an OH and an OR. You have the two alcohol groups both add. Your byproduct is water, so in order to drive the reaction to the right, you're going to have to remove water as you go along. This final product is called an acetal. So you can see the middle is the hemiacetal, and this one is the acetal. So let me show you what the mechanism looks like for this. First thing looks like the same kind of step as it did when we were doing acid catalyzed hydration. So your oxygen here with its two lone pairs is going to add to the acid. Your electrons go out on the A, and so now you have a protonated ketone or aldehyde. We also know that this has a resonance structure that looks like this, which makes that carbon more electrophilic. Our second step is nucleophilic attack and deprotonation. So first step, we protonate the carbonyl. Second step is where our nucleophile attacks. So here's our OH with our electrophilic carbon. We bring in our alcohol. The alcohol attaches, and now we have OH up here, OR group, H down here. That oxygen is positively charged, and so then some sort of base, either water that's in solution or another alcohol that's in solution or something similar, will come in, deprotonate, and you'll have your hemiacetal. So there's your hemiacetal. Here's how it continues. Once you've formed your hemiacetal, you're still in aqueous acid. And so another H plus can come in and add to this oxygen. So this oxygen can come in and add to this H plus. After the alcohol is protonated, it makes it into a good leaving group because now you have water. Your water leaves, and now you are left with the carbocation. These electrons come down here and form a double bond. Right? So this is a resonance structure for us. Possible resonance structures. So that was our third step, was elimination of water. Here comes our fourth step. Our fourth step is nucleophilic attack and deprotonation. So if we have our carbocation, here's our alcohol. Our alcohol can come in and attack here. Now we have our carbon with our OR group, OR up here. It still has its hydrogen on it. It's still positively charged on that oxygen. And so now a base will come in, remove that hydrogen, and the electrons will go back onto the oxygen. And so your final product is an acetal. It has an OR here and an OR down here. This is a reversible reaction. It's important to notice that because you can treat an acetal with aqueous acid and make it go backwards. So you can follow the mechanism backwards, one step at a time. The carbon between the oxygens that you see here is the one that will end up being the carbonyl carbon. Excuse me. When you do the reversible reaction. So, for example, if you have this particular acetal and you add water and acid, you can end up back with cyclopentanone and 2 of your alcohols. The nice thing about this kind of reaction is that this makes acetals a good protecting group for a ketone. You can put them on and then you can take them off. So if you're trying to protect ketones from things, acetals work well. You may have seen some of these in your pet molecule papers. For instance, if you use this as your alcohol, you have both alcohols in one molecule connected to each other, and so you can end up with cyclic acetals. So for instance, if we wanted to protect cyclopentanone that way, here's our cyclopentanone, we could use that particular acetal. We would use, so that one, you can use para-toluene sulfonic acid as a good acid source, and your product would look like this. So you'd have your oxygen and your oxygen, but they just happen to be connected by 2 CH2 groups in the middle. You can also form cyclic hemiacetals. So regular hemiacetals are unstable and are going to go all the way to the acetal, but cyclic ones are stable, and you can form 5 and 6 membered rings this way. You get an intramolecular cyclization of hydroxyaldehydes, and these can be acid or base catalyzed. So let me show you a picture. Here's your hydroxy group. Here's your aldehyde group. I'm going to start counting my carbons. So I have 1, 2, 3, 4, 5 carbons in between the carbonyl, including the carbonyl and the oxygen. So if I put them together, if this alcohol here attacks my carbonyl, here's what my ring is going to look like. So you can do it acid or base catalyzed, but it's going to be the same idea as forming our hemiacetals before. And so our ring is going to look like this. You have 1, 2, 3, 4, 5, 6 members in your ring. One of them, or 5 of them are carbons. So there's carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. That 6th member of your ring, right here, is going to be an oxygen. That's the oxygen from the alcohol. So we know that, first of all, our carbonyl was coming off of our 1 carbon. So that's where we're going to have our OH now. And secondly, we had a methyl group coming off of carbon 2, so that methyl group is still going to be there. So that's what our cyclic hemiacetal looks like. It's going to make a racemic mixture. You're not going to have a stereogenic center here because it can attack from either side. But that's how it works. You can convert these hemiacetals to acetals with alcohol and an acid, just like you would convert a regular hemiacetal to an acetal. So let me show you the mechanism for that. Here we have our cyclic hemiacetal with our OH. Here's our acid. Same thing that happens. Our OH is going to attack our acid. OH2 plus. This can leave. Now we have our O is still here, but now we have a positive charge here, a carbocation. Resonance structure can be drawn, but we'll just go from here, and you'll see that if we bring in our methanol, CH3OH, here's our methanol. It's going to attack where the carbocation is, or whatever alcohol you so desire. O, CH3, H, this is still positively charged, and so then your base can come in, your other alcohol, etc. can come in, and you can form the acetal. So this was our carbonyl carbon to begin with, and it's bonded to an oxygen here and an oxygen here with carbon groups coming off of them, so that's what makes it an acetal. This only works for hemiacetals that have alcohols that are resonance stabilized via their carbocation. So it's not going to work just for anything to lose a water. It only works for acetals because this carbocation is resonance stabilized right here. There's its resonance structure. So because it's resonance stabilized, it can then form its acetal. And that's the end of this chapter. Hope you have enjoyed chapter 21. Look forward to seeing you in chapter 22.